Okay, thanks very much, Mike. Well, good afternoon, everyone. I'm actually greeting you from Sheffield at the moment. I don't know if anyone's further afield, but possibly good morning and even good evenings in order. But you can see from this title slide, I'm just going to be talking a little bit about stainless steels, particularly the properties and grades that are used in the marine environment. As Mike said, I'm not involved full-time with the BSSA these days, 50% of my time. The rest of the time, I'm working for my own company, providing on-site and online technical courses. I'd probably encourage everyone to stick with the format and ask questions at the end. And even after the end, you'll see I leave my telephone number and email addresses, so everybody can contact me even if a question doesn't quite get through. So let's just move on, and I'm just giving you a quick summary of what I'm planning to cover. I like to start with one or two definitions and just say something about the types of stainless steels that are out there. I'm conscious that many people are only aware of 304 or 316. I'm guessing the audience here will know of quite a few more, given the demanding environment the marine environment is. But I'll go on after saying a few of the basics. I'll say something about the grades that are typically found in the marine environment. Then talk a little bit about corrosion. A big subject, in fact, all these summary points are big subjects. So I'm just hoping I've chosen a few areas that are relevant to everyone that's out there. Again, a few tips on good performance with fabrication, or at least not every method of fabrication, but I'll touch on machining and welding. And hopefully, if I get my timing right, we can just look briefly at a few case studies. So let's just start with a little bit about stainless steel. And it's always nice to put us all on the same playing field. I like to just say what stainless steel is. A definition does actually come from the Harmonized European Standard BSEN ISO 10088, and it's a steel that contains at least 10.5 weight% chromium. You'll see why that's important later, but briefly I can just say now it's considered the minimum amount of chromium needed to ensure a continuous passive layer forms on the outside of the material. As soon as the material is produced, oxygen in the atmosphere reacts with chromium on the surface and gives you this protective chromium-rich passive film. The neat thing about that is if it's scratched or damaged, a new virgin material's revealed, the oxygen will react with that and recreate that protective passive layer. So in principle, if the material is not exposed to anything really harmful, it should always be protective. Okay, there's several families of stainless steels that we can choose from. The 4 families here are identified. And apologies if some of the terminology I use sounds very technical. It's just that you can't really get away from certain terminology when we're trying to differentiate the types of stainless steel that are out there. But in all these slides, there's a few brief pointers as to which are good or bad with respect to particularly corrosion resistance. You'll see on this slide, we've got 4 families named: martensitic grades, ferritic grades, austenitic grades, duplex grades. No doubt the ones you're most familiar with are the austenitic grades. They exhibit excellent corrosion resistance as long as the passive film, the protective surface layer, isn't destabilized in some way. And you can guess what I'm going to come to, because we're talking about a marine environment, and we know there are species in the marine environment that's particularly going to disturb that layer. There are a couple of categories it's worth drawing attention to in the austenitic area. There's standard austenitic grades, the big 2 I'm sure you've all heard of, 304 and 316. Very good level of corrosion resistance, but we can go to even more highly alloyed grades, a category of austenitics we refer to as super austenitics. You may or may not have heard of grades like 904L or 654 SMO, but they've got even better corrosion resistance, and you'll see why that comes into play a little later. Duplex grades, described by some of the big producers these days as the new boy on the block. I mean, you know, developed in the 70s and 80s, and particularly relevant to the marine environment, particularly standard and super duplex grades. And again, I'll qualify that more later. And although duplex grades were discovered in the 30s and 40s, they were never really commercially developed on a commercial scale until much later, as I say, the 70s and 80s. So just to put a bit of context to that, martensitics and ferritics, we're only talking about iron chromium compounds. The difference between ferritics and martensitics is essentially the amount of carbon that we've got in there. A big difference between martensitics and the ferritic and austenitic grades is the high hardness. They're usually chosen for applications where very high strength's needed. Hidden in the martensitics there, and the bottom left, you'll see pH 17.4. Now, I often describe that as a separate family. I mean, in truth, the basic structure of the material is the same, but some of you may be aware that pH stands for precipitation hardened stainless steel. So there's a subcategory, if you like, under martensitics, which are a very high-end special group of materials that tend to be used more in, well, they're certainly used in the marine environment, but particularly demanding market sectors, you know, whether it's aerospace, power generation, marine, as I've already said. I'll probably just draw attention to one thing. The duplex grades, some of you probably already know, I mean, duplex, it suggests two of something. Well, it turns out that the structure of a duplex stainless steel is pretty much 50% ferritic, or it's got 50% volume percent ferritic grains, 50 volume percent austenitic. But rather counterintuitive, it doesn't have properties that lie somewhere between the ferritics and austenitics. They've typically got double the strength of austenitics, and because of other certain alloying additions, many of the grades have superior corrosion resistance to the standard austenitics. So already I'm sort of, if you didn't already know, broadening out the range of stainless steels that are available for specific applications. Let's just briefly look at those families in terms of properties. Again, some of you may have seen stress strain curves, the kind of data you'll generate in a tensile test. You may be familiar with the form of these curves. There's a couple of arrows on there pointing to properties like the 0.2% proof strength, and the peak of all these curves is the point we've got the tensile strength, or commonly referred to as UTS, ultimate tensile strength. And you'll see as we go through the families, the line on there that's typically consistent with 316, you'll see it's got a relatively low proof strength compared to other types. Ferritic, higher proof strength, duplex, higher still, and we go to the martensitics and a pH, precipitation hardened steel, the curve labeled D, and strength is going up. You'll also see ductility is going down. So you sometimes find that the harder the material is, certain product forms might not be readily available just because of some of the difficulties in the processing aspects. And very quickly, another pertinent point is ductile brittle transition. I'm not going to go through in great detail on the slides because they're all points you can pick up to me at your leisure, whether it's at the end of this presentation or at any time. Because one thing about the BSSA, we do have a technical advisory service, and it's free, so you can ring or email anytime you want. But the point on this slide, you'll see that all those families, with the exception of the austenitic, the origin band, they all have a big interruption in this plot that shows impact toughness versus temperature. So if we're talking about any applications that where components are exposed to very low temperatures, there's only one family you're going to select the material grade from, and it's going to be an austenitic. Of course, duplex grades, you know, have transitions going from behavior that's essentially ductile to brittle at fairly low temperatures, you know, -50 and lower. So that's not really going to trouble us. You know, it's not going to prevent us selecting those in certain marine applications. Okay, let's move on. A sort of snapshot of the volumes of the different families or types of stainless steel that are out there. You'll immediately see from this bulleted list that most of what's out there in terms of volume, and because the densities don't change significantly across these types, whether we're talking about mass or volume, most of what's out there is austenitic, 70%. Ferritic, the next big type, certainly not that prevalent in the marine sort of area, 20%. But the more sort of specialist materials like duplex, precipitation hardened, martensitic grades that are chosen specifically for a very favourable property, in terms of volume that's used, significantly lower. But that's not to underplay their importance. It's just that they've been tended to have been developed for specific applications. Duplex, not least for certain grades, super duplex grades for subsea applications. And to some, it might seem a little bit academic, showing how the structures vary. But the reason I sort of always include this slide is I draw attention to the fact that when we're talking about a different type of stainless steel, whether it's austenitic, ferritic or duplex, the reason the properties, the physical properties and the mechanical properties are all different is because each type has a very different crystal structure. The metallography of the material looks very different. You know, we can talk about ball and stick models of atoms, not so important, but it's fundamental just from the point of view of knowing that that's the thing that actually impacts the properties. Okay, grades used in a marine environment. I'll probably throw in one or two anecdotal points that come from lots of inquiries we get. We regularly get inquiries of, you know, what grade of stainless steel should I use on a building as a panel that's exposed to the coast, or I'm wanting to fix something on the deck of my boat and I'm thinking of using this grade. Well, there's certain starting grades that when it comes to marine atmospheres, but I'll just take a step back and just say something about the marine environment, because you'll see later I'll make a comment about this phrase marine grade stainless steel. It's not a particular phrase I like, and I'll explain that a little bit more later. But if we just look at the basic composition, say, of seawater, we immediately see there's a lot of salts in there, not just sodium chloride, but other metal salts. Those salts are obviously very significant because the conductivity of seawater goes up, and corrosion is driven by electrochemistry, by electrochemical reactions. And if the conductivity goes up, the corrosion currents go up. So reactions that are at the base of corrosion are actually driven harder just because of that conductivity. To put it in perspective, deionized water has got a conductivity about 1/1,000,000th of seawater. Tap water varies to 100 to 1,000 times less conductive than seawater. And if I just go on to some data that's often shown to sort of show the different levels of aggressivity there are in the marine environment. This is a curve. It shows the relative corrosion rate, or in this case, it's labelled relative loss in metal thickness, and it's harbour piling. It references harbour piling. But you'll see immediately there are a number of zones. The first one, zone 1, is the atmosphere. And you can see if we're high up in the atmosphere where there's less chloride dissolved in moisture, the corrosion rate is lower. As we come down to the splash zone, it increases. So we get a peak actually in corrosion, or at least a peak in the aggressivity of the environment, where we've got high chloride, but in the splash zone we've also got erosive effects of the waves. Then there's a drop back because those things aren't as relevant, but then we find there's another peak just below the mean low tide level, and that's due to two things. One, microbial activity. An important aspect there is sulfate reducing bacteria. But there's also an impact of galvanic corrosion as a result of differential levels of oxygen. So we get an accelerated low water corrosion rate just below the mean low tide level. Then we drop off as we get to the mud line or the seabed because the level of oxygen goes down. If there's no oxygen, you're not going to get a corrosion process. So these zones highlight that there's different environments encapsulated by the thing we might refer to as the marine environment, which sort of gets onto that term that I don't, it's just a personal view, I don't particularly like it, this term marine grade. I'd sooner know precisely what grade I've got and what the service environment is that a component for a particular application is going to be exposed to. And you might possibly, if not all of you, some of you have had my experience where you go and buy a part in a chandlery, somebody tells you it's made of marine grade stainless steel. Well, the first thing I say is, and what grade is that? They usually think it means 316, and more often than not it does. But it might not be good enough. I mean, 316 is what I'd consider the starting grade to use for components that are going to be exposed to the atmosphere, but it may not be good enough for a component that's going to be exposed in the splash zone. It's certainly not going to be good enough submerged below the waterline, unless there's some sort of protection involved. And we'll come on to things like that later. Okay, a question I remember once posing at one of your annual dinner events at Regent's University, I believe it was some years ago, is how many grades of 316 are there? Not many people appreciate there are quite a few grades tagged with 316, and some are more corrosion resistant than others. I just put a table up here that shows you some of the compositional differences. If you see nitrogen go up or molybdenum go up in the particular grade, the corrosion resistance goes up. And again, I'll qualify that a little bit later. But you'll see here 316L, which I'll also explain later. You'll see there are 3 different EN numbers, 3 different grades that all have the tag 316L. I suspect if somebody gives you something called 316, they'll tell you that you'll probably be getting the leanest version of 316, because it's usually the case that if you ask for something else that you know is going to be more corrosion resistant. For example, you'll see there's 2 316 grades that have got between 2.5 and 3 weight percent molybdenum. Those 2 grades are going to be more corrosion resistant than the one that's got 2 to 2.5 weight percent molybdenum. Again, the detail of that will come out later. It's also worth reminding you of the expensive elements like chromium, molybdenum and nickel. Although there's a lower and an upper spec limit on all these grades, the mills have got tight enough control on the grades to ensure the amount is very close to the lower spec limit. Because obviously if they're producing hundreds of thousands of tons, that would be money thrown away if they always pushed it to the high limit. you know, money's obviously important to everyone. And if they can put less of those things in, they will. I mean, that's the main thing, is that it is at least within specification. Similarly with 304, there's more than one grade with that tag. And we also have cast grades. I'll quickly say that if someone asks me about what grade this a component should be made from in a marine environment, and I'm talking about a marine atmosphere, unless somebody's not the least bit bothered about aesthetics and it's not a safety critical component, I wouldn't generally recommend 304. That's not to say you won't find 304 used out there, but you'll soon know if you've got 304, because it won't take long for the surface to degrade. I'm reminded by an inquiry who, well, he was a guy who went diving, fitting fasteners to the anchorages and fixtures of fish farms located in Scotland. And I think it was every 2 or 3 months he had to go diving to replace 304 fasteners that were securing these fish farms, or fish farm cages. And he was asking me if there was something better. And obviously 304, I wouldn't consider it the best material to choose for an atmosphere, never mind subsea. And there are always grades to cope with the environment, but you've just got to have a little bit of awareness sometimes of what mechanisms can undermine performance, and what grades would be fit for purpose for that particular environment. So just to actually label a few grades that some I've no doubt you will be well familiar with, and some maybe not, and where we'd start using them. 316, I've already said, a marine atmosphere. As soon as it comes in contact with seawater, assuming it's an application where protection by sacrificial anodes or even impressed current techniques is viable. And it says there, the middle section, you know, if we're talking about hull mounted equipment, impellers, prop shafts, we would have to protect those materials. 316. Well, to put it in perspective, I didn't draw attention to the chloride in seawater earlier on the slide, but there's pretty much 3.5 grams of sodium chloride in every litre of seawater, which means the ppm is 35,000 ppm chloride typically in seawater. And 316 would only be recommended normally in environments that have got not more than about 1,000 ppm chloride. So immediately you know you're testing the material if you're just immersing it in seawater, hence the need for galvanic protection, but not just on 316, on a significantly more corrosion resistant material like 2205, which is referred to as standard duplex and used in prop shafts, for example, that would need protecting too. 17.4 pH precipitation hardened martensitic grade, that's least corrosion than any of those in that middle list, so not surprising that needs protection. But there are grades that can survive seawater conditions without any protection. But there's 2 categories essentially: the super austenitics and the super duplex grades. Again, I'll say more when we get onto the corrosion why those are particularly useful if you want to make something that doesn't need any protection. So, I mean, I've already alluded to the fact that grades can corrode, but it's just worth making the point that the important thing is understanding the steady state operating conditions and then knowing which grades are can deal with that operating environment, and knowing what deviations there might be, you know, the extremes of conditions that the material is going to be exposed to, and indeed changes that might occur over time. I mean, we're often asked to recommend a grade for a particular application that will last 20 years, 50 years, even 100 years. And although we can tick a certain number of bases, one thing I usually say is, could you give me an idea how the environment might change over that time? I mean, nobody usually can. And often people come to the conclusion, well, okay, let's pick the best grade we think will be fit for purpose now. And in 100 years' time, we won't have to worry about it anyway, because we won't be here. A little bit of a glib comment, but sometimes if you have to choose something, particularly if it's a safety critical part and you don't know how things are going to turn out in the future, it may be worth considering over engineering the thing from a material selection point of view. I don't usually advise that, because there's usually an answer once all the facts are in. Anyhow, just a point about you know, stainless steels do corrode. I know probably everyone listening does appreciate that, but we're quite regularly faced with people saying, I bought this stainless steel, I used it for that, and it's corroding. It can't be stainless steel. Well, every engineering metal corrodes. It's just about understanding what the conditions are that are going to bring about some level of corrosion. Well, let's look a little bit more at corrosion itself then. Some of the mechanisms, and there isn't really time to go through everything. So I've sort of chosen the rather common corrosion mechanisms. Uniform corrosion I can quickly deal with in the context of stainless steels, but I'll focus more on pitting, crevice and galvanic corrosion. I mean, if anyone wants to come back to me at any time, whether it's right at the end of this presentation or by email through BSSA, you can raise any corrosion mechanisms or issues with me or my job share partner, Dr. John Butler. So even if you email me, it could be my colleague that comes back to you. You can raise any of these areas with us at any time. So I'm going to deal with just the three that I mentioned mainly, but I'll just mention something about uniform corrosion first. I mean, as far as uniform corrosion is concerned, it's the chromium that is a big factor in preventing it. You'll see this plot just shows you a plot of corrosion rate. I'm not going into the details of how these corrosion rates are being measured, but it's corrosion rate versus chromium content. And you'll see that cutoff, 10.58% chromium, which I said was a minimum amount that had to be in a steel we call stainless steel. You'll see that anything below that, so if we're at the mild steel end or low carbon steel end, where we may have no chromium or only 1 or 2 weight%, you can see the chromium, the corrosion rates are very high. But as soon as we start adding chromium, as soon as we're at about 2 or 3 weight%, the corrosion rates drop quite dramatically. You can see that above 10.5, we're pretty much plateaued, and that's because we've got a continuous chromium oxide layer protecting the material. So uniform corrosion doesn't affect stainless steels, certainly not in a marine environment. It tends to only be a factor when the material's been exposed to really aggressive chemicals like concentrated sulfuric acid or something like that. So obviously we're well away from that. So we don't really have to worry about uniform corrosion. The thing we have to be concerned about is localized corrosion mechanisms. You'll be familiar with ways of preventing uniform corrosion. You might actually choose a stainless steel to avoid it. The bottom line on here, choose an appropriate passive film material. Other ways are actually using something like galvanized steel or sacrificial anodes or painting or use of coatings. So let's just demystify some of these mechanisms. Pitting and why it's quite prevalent in a marine environment, even on something like 316 in atmosphere. I've bestowed the virtues of this passive layer, this chromium oxide layer. Unfortunately, one of the Achilles heels, if you like, of any passive layer metal, and the same goes with aluminium alloys, one of the Achilles heels is chloride, presence of chloride. It's a very mobile, small ion that destabilizes the bonding in oxides. So it causes that nice protective chromium oxide layer to break down. And as soon as it breaks down, the corrosion mechanism itself, or the electrochemistry that's operative once that protective layer is broken down, actually produces hydrochloric acid in the pit that occurs. And as the pit develops, the concentration of hydrochloric acid gets stronger. So actually, the pitting can rapidly accelerate. Now, a monolithic component, you might be able to live with it, but if it's something like a tube carrying some liquid and the tube wall's breached, well, that's it. The component that, you know, certain components would need replacing straight away. So chloride and pitting and stainless steel's quite a prevalent thing, unless you choose a grade that's particularly resistant to it. Now, this next slide just identifies something we call the PREN number, or the pitting resistance equivalent number. The bottom line is the higher that number, the more resistant to pitting the stainless steel grade is. As a sort of fairly arbitrary rule, if the pitting, the PREN number is above about 22-ish, you're in a reasonable position for exposure to the atmosphere. So there's that dashed line there, the lower blue dashed line, just shows you that 316 is above that line, 304 is beneath it. But a lot of these things is to do with maintenance. I mean, if you're regularly washing salt deposits or debris off parts that are on the deck of your boat, the longevity of the material, even one that's less corrosion resistant, will be better. But you'll see as we go from something like 316, which is in the middle band of grades there, the red line, as we move up to something like 904L, which is one of the more corrosion resistant grades we pointed out to on the marine application slide, we've got a significantly higher pitting resistance, a PREN number. And we can go to, and as I say, 904L's termed a super austenitic. We can get more corrosion resistant than that. The second blue line, the one marked at 40, is typically the line you've got to be above for good performance subsea. So if you're below the water line and 254 SMO, I wouldn't expect it to be a grade that people have heard of. 2507, which is a super duplex grade, you may have heard of, but those are the kind of grades that are used in critical parts on oil and gas platforms, but also components in critical structures and vessels that are permanently immersed. You can guess a cost comes with that, and so usually people are, well, they're really trying to choose a grade that costs the least, but at least is classified as being fit for purpose for that application. But as I said, that does require an understanding of the detail of the operating conditions, and maybe an appreciation that a certain level of maintenance is required as well. Another metric that goes with the PREN number, or the pitting resistance equivalent number, is the critical pitting temperature. That's the temperature below which you won't get pitting. And you can immediately see on this table, going from, you might not recognize it as such, but 430 is a ferritic grade, 304, 316 are the big two austenitic grades. As we move down that table, the critical pitting temperature goes up. So you can see immediately 304 is very likely to pit above 10, 316 above 20. So you're in a safer and safer ballpark, you know, 2205, a duplex. We wouldn't expect to get pitting below about 30 degrees. So you'd be very safe with that, even in our sort of more tropical zones. Ways to prevent pitting. Well, obviously chloride. I think I particularly mentioned chloride, and I mentioned the level, the maximum level we'd expect 316 to perform well at, and that's 1,000. 304, it's only between about 100 ppm to 300 ppm chloride, which is one of the reasons why it's not usually a starting grade I consider when people are asking me about materials to use in a marine atmosphere. So first, understand the operating conditions and look to choose a grade that you're comfortable or happy will survive it. Those metrics, particularly the PRE number, there's widespread references to those. If it's easy enough to work out, there was an empirical formula, I didn't draw attention to it. The PREN number is just based on the concentration of the weight percent chromium, molybdenum and nitrogen in particular. So it's just an empirical formula. The numbers themselves for all the grades that are out there to choose from, you know, easily referenced. I think that probably deals with that. There's a point about recognising environment, you know, the aspects of the operating environment that might change, which I'd already mentioned before. Okay, crevice corrosion. As the term suggests, wherever there's a small gap, a narrow gap, and you can see from these components, particularly that nut component and the washer, that even the gap between a washer and some sort of bulkhead is a potential crevice. I mean, a definition of a crevice really is a gap that's got an aspect ratio such that a microenvironment can develop in that gap that's different to the external environment. Unfortunately, when you get gaps like that, very quickly those gaps get filled with dirt or debris. If you add chloride in there, you very quickly end up with an environment where oxygen can't readily diffuse to the stainless surface, so the passive layer breaks down. Add in chloride, that accelerates the whole process, and it doesn't usually take long before some level of corrosion occurs. You'll see that the other two examples, you know, a huge area corroded away under a flange, and a huge part of the load-bearing cross-section of a bolt, both of which you wouldn't see, the flange or the bolt, you wouldn't see the damage until something critical happened, either the pipes leaking some noxious liquid or the bolt, whatever structure it's supporting, collapses. So you'll see in certain cases, it's very wise to sort of understand these things, the operating conditions, whether there's a risk of these corrosion mechanisms, and choose material that will combat, well, at least help you to mitigate the risks. Ways of preventing crevice corrosion. Well, again, we can choose the right material that's fit for purpose that we know is very crevice corrosion resistant. There are other ways of preventing crevice corrosion, not least if we're talking about a fastener, we could use compressible washers that really just fill the gap or close the gap, just prevent there being a gap in the first place. Yeah, I'll move on because I'm aware I'm a little bit behind, so I want to catch up some ground. Galvanic corrosion, again, this is a very simplified list of metals in order of the most anodic to most cathodic. And there's a few simple rules. Avoid putting different metals together because different metals in contact generate a voltage between them. Now, in the list, the further away two metals are, the bigger the voltage that's generated, which bigger voltage means ultimately if those materials are in contact with an electrolyte, and there's always an electrolyte, there's always water around, even if you can't see it. We know there's plenty of water in a marine environment, but even inside a building, you'll always have layers of water, maybe a few molecules thick, that you can't see, but there's always a means for current to flow. So so you know, one rule of thumb might be avoid putting two dissimilar metals together. Obviously you can't always do that, so where you can't, you try and choose metals that are close together in the series, because if they're closer together, the voltage across the junction of the two metals will be smaller, so any currents that flow will be lower and be driving the corrosion process lesser, if you like. I've already mentioned some of the ways of avoiding it, but there's just a footnote here about galvanized steel, which will suffer corrosion too. I mean, the zinc's on galvanized material. I think many will appreciate it's there as a sacrificial anode. It corrodes at the expense of the steel it's covering, usually plain carbon steel. But if it's damaged, there'll be a local area where it's not protecting the steel. Or what do we do with cut ends? Often galvanized material is cut, and we can paint it, yes, but paints themselves can degrade. There's always answers to the questions, and I can't always give a specific answer. I just talk in generalities until someone says, well, this is a situation, how can I sort of mitigate the risk of some type of corrosion occurring in this situation? The other thing is that when zinc corrodes, that zinc can get in the aquifer, or a aquifer, and that can produce its own toxicity issues. Some brief points about fabrication, and actually this is quite a slim section. There's lots of things I could cover. I mentioned earlier that both these areas are very big. I picked two that I thought might be of interest: machining and welding. It's a bit debatable whether the machining is well, I'll explain what I mean shortly, whether it's so relevant, but I'll qualify that. Let's just talk generally first when it comes to fabrication of stainless steels. I mean, stainless steels, we can cut them, press them, bend them, weld them, machine them, just like we can non-stainless steels. But a big point to be aware of, and I'm sure people, if there's anyone out there regularly working with stainless steel, a big point is relative to non-stainless steel, particularly mild steel, it's a high value material. So you want to reduce waste, and you don't want to unwittingly cause any corrosion, level of corrosion through just poor work practices. So one of the big things, and although this point is out there widely, it often comes up as regular as clockwork. The thing to do whenever you're working with stainless steel is segregate any work you're doing with stainless steel from any other non-stainless steel activities. So anything being done with mild steel and stainless steel in any workshop should be well segregated, and never use tools that you've used with mild steel, whether it's grinders or wire brushers. Never use those also for stainless steel, because you'll just transfer the more anodic steel, the mild steel or low alloy steel, and it'll contaminate the stainless steel, and that'll just promote points or sites where you get the start of some sort of galvanic corrosion activity. The other two general things I'd say is, particularly when heat is involved, certain thin sections of stainless steel can suffer distortion. So we'll talk about that when I get into the welding proper. And so some sort of restraining support jigs are needed. And there's another last line on this slide that somewhat steals my thunder from another slide. If any process causes heat tint to be produced on a stainless steel, if you want to restore the equivalent corrosion properties, you want to remove it all. So very quickly on machining, there's always the problem with particularly austenitic grades is they work hard and readily. They're difficult things to machine, or certainly if you've got experience machining non-stainless steels, the work hardening means you've got to carefully look at machining parameters. It's also worth pointing a rather obvious thing. It's not always considered, but you want to choose conditions that eliminate any machine vibration or risk tool chatter. Now, I'm just familiar with tap testing, where you can look at the whole frequency dynamics of the tool in the workpiece and the machine and see where you've got a frequency response that minimizes vibration. I mention it mainly because it's quite counterintuitive. Usually if there's vibration and chatter on a machine, say a turning machine, people immediately want to slow down or cut down all the parameters, you know, lower the depths of cut, lower the feed, lower the revolutions on the turning part. But sometimes actually you'll find there's less vibration, you'll find there's lobes of lower frequency response at higher parameters. So it's just worth being aware of that. The other things are the obvious things, you know, using sharp tools, negative rake angles with stainless steels, particularly because it just puts more of the load in the heavier body part of, whether it's an indexable tooling insert or not ever, it just puts more of the load in the body of the tool. And lubrication, you know, I'm sure any machinist out there will be familiar with lubrication, cuts down cutting forces. And very quickly, there's two slides that just point to, there's always grades that have been designed to give you better productivity in a machine shop. The caveat is that all free machining grades, they rely on an increase in inclusions, so elevated sulfur. That immediately means in a marine environment, it's not going to perform so well, and it isn't something that I'd recommend being exposed even to a marine atmosphere. I mention it because I know people have been sold free machining grades because they wanted to produce more components that ultimately were going to be exposed in a marine environment. So I'm sort of touching on this as much to alert you to the fact that free machining grades have got lower corrosion resistance compared to their standard counterpart. But you'll see here standard grades significantly lower machinability indexes compared to low alloy or mild steel. You know, if we use that as the base, low alloy carbon steel, the blue bar with 1, you'll see that something like 2205, a duplex grade, it's cut by half. 304, similar, 0.52 compared to 1. So sometimes you just have to learn to live with the difficulties, but be particularly mindful of machining parameters. More data on duplex, and pointing to the fact that we don't necessarily just have to stick with cementer carbides, which are probably the most widely used cutting tools. High-speed steel cutting tools are still used, particularly particularly for intermittent cutting, and for troublesome materials like stainless steel, because high-speed steel is significantly tougher than carbides. Let's just look at briefly at welding, and I'm just looking at the time, and I'm conscious. I'm just going to touch on 2 problem areas, as well as saying what's good about welding stainless steel, or a particular family like the austenitics, and I might jump to 1 or 2 case studies after that, because I just want to keep time on track, and we're not going to have much time for questions if I keep going at this slower pace. Anyhow, welding properties. I'm just going to stick with austenitics. The good thing about austenitics is very good to weld. You can readily weld the material in thick sections, unlike ferritics. And unlike martensitics, which are the only heat-treatable family type, we don't have to worry about preheating the material or post-weld heat treatments. So that's a big plus. They're very readily weldable. There is one caveat. It's circumvented by the L grades. You may remember in that 316 list we've got 316L mentioned several times. The L stands for low carbon. Now that's very useful because there's a critical temperature window between about 450 and 900, where if carbon's high, we can get formation of chromium carbides at the grain boundaries, which effectively depletes chromium from the grain boundary area. So subsequently, if that material is exposed to an adverse environment like marine, the first place it's going to get attacked is the grain boundary. So I always draw attention to the fact if any welding's being done, you want to use either a low carbon grade, an L grade, but we could also choose another option and use what we call a stabilized grade. That's a grade with either titanium or niobium in. So a good type of stainless steel to weld. You'll see the potential problems: weld decay, weld metal solidification, distortion. Let me quickly go to the weld decay because it touches on the sensitization issue that I just said. If we do get this chromium carbide formation, because we've heated the material up through the welding process, and subsequently it's exposed to an aggressive environment that promotes intergranular corrosion, you'll see the kind of thing we can ultimately end up with. Here we've got a pipe component. The heat affected zone has just become eaten away because the grain boundaries have been attacked and the grains have essentially fallen out. This is a schematic and a photograph of a real surface that actually was sensitized or was subject to conditions that promoted intergranular corrosion. So, you know, we know about it, it's widely known, people still make the errors, but it's very easily dealt with. We either use low carbon grades, so there's not enough carbon to combine with the chromium cause that problem, or we use a stabilized grade. That's a grade that's either got titanium or niobium in it. And the reason that helps is titanium and niobium have got a higher affinity for carbon than chromium. So they combine with the carbon and we don't, and the chromium's left intact at the grain boundary. So essentially there's no depletion of chromium at grain boundaries. One other quick thing before I jump to what, a couple of case studies. I might just stick with one case study because I've done rather poorly with time. Weld metal solidification cracking. It often occurs as a result of presence of impurities like sulfur and phosphorus. Now, a key point is, particularly when we're welding austenitics, it's an advantage to actually choose a filler metal or conditions that actually give rise to a little bit of ferrite in the weld seam. The reason is the ferrite's got a higher solubility for things like sulfur and phosphorus, so it acts as a kind of sink, if you like, and those deleterious kind of elements are removed. If you don't have that, sometimes you can have low melting point glassy phases that combine sulfur and phosphorus, just segregating at grain boundaries, and if that happens, you just have very weak grain boundaries. So weak that just on cooling you can develop cracks in the weld seam before you've even put the material to an application. So there are things to look out for. I'm deliberately going to jump now. A quick point about effective heat tint. If you've got any sort of discoloration at a weld seam, what you know you've got is a thick chromium oxide layer beneath which you've got parent metal that's depleted in chromium. So you know that if that material was subsequently exposed in an aggressive environment like a marine environment, chloride is going to get to that depleted parent surface, the parent surface depleted of chromium. So it'll perform much worse than it otherwise would. I'm going to jump through there. I'm just going to deal with a couple of case studies. This is probably something you've seen many times on boats you've inspected. Jubilee clip rusting away. You might regard this partly a combination of you know, poor choice of materials or poor maintenance. Interestingly, that Jubilee clip, for example, it looks like it's a galvanized material because you've got a lot of white powderous deposit on it, which is synonymous with zinc corroding. I'm sure your advice, or many people's advice out there, would be use stainless steel Jubilee clips. I'd certainly be expecting people to recommend 316 Jubilee clips, but again, if this is Jubilee clip on a gas hose hidden behind a galley cooker, if you never look there, you're never going to see what's happening. But given it's a critical part, you know, you don't want the gas pipe to be leaking. Simple maintenance can solve a lot of problems. Washing things off, checking if there's any sign of degradation. If you've chosen a cheaper material, at least be ready to replace it. I mean, interestingly, there's what looks to be a stainless steel head there next to the heavily corroded nut on the Jubilee clip. And obviously that's getting covered with debris. You can even see the beginnings of tarnishing on the inside of that. But it looks a little bit of a horrible situation to me. And it's certainly something you'd want to take the right measures to avoid, I think. I'm going to skip that one. I'm just going to jump to which potentially I'd argue is more serious. Crevice corrosion, the other one, an example of galvanic corrosion. You could argue poor choice of materials, poor practices as far as inspection and maintenance is concerned. This is a crevice caused by poor fitment of a propeller on the prop shaft. You can see the keyway and you can see what's happened for the poorly positioned or wrongly positioned prop. We've got a very deep groove eaten away as a result of crevice corrosion, and it turns a corner and actually the corrosion runs down towards the keyway. So, you know, potentially quite serious, because whenever you get corrosion like pit features or crevices, particularly if it's a load-bearing part, those features act as stress raisers. The next thing you'll find is you've got fatigue cracks growing. Although this hasn't cracked apart, you know, you wouldn't want to ever run the risk of things like that. So again, I guess really it's about poor practice and maintenance. You know, if you take your boat out once a year, you'd expect to pick up on things like this, but I'm conscious that lots of people do neglect to even look at things, or boats are left sitting in the water for many many years in some cases. I better quickly wind up there because I'm just on the hour and I think I've sort of breached your routine. But I'll just draw attention to two slides. One is courses that I run and BSSA runs. You can read them at your leisure. But contact details for me at both companies are on the last slide. So you can contact me whenever, or my colleague, if it's about issues to do with stainless steel and anything else really. I mean, we'll either know the answer quickly or we won't. So thanks for listening, and very sorry I've sort of took up a bit too much of the time, but I'll pass over to you then, Mike.
No, nothing to apologise for, Mike. In the nicest possible way, hearing you speak, it's always like going back to school. It's brilliant. So thank you for what you've delivered. I've got one question from Mark, just to wrap the session up. Yeah. He asks, instead of welding, would you prefer explosion technique for connecting two different materials? This is often seen on the aft deck cleat area, for example.
To be honest, explosive techniques it's not particularly my forte. I think where you've got less, I mean, obviously welding, typically you've got a filler and all sorts of things can go wrong with our welding techniques. My temptation would be to say, yes, it sounds in some circumstances a more prevalent method, but I wouldn't want that to be the answer. I mean, it's not a technique I know well. And I think whenever you investigate any techniques, they all come with their own pros and cons. I know I've certainly seen some beautiful interfaces produced by those kind of explosive techniques you're referring to. An interface, no gaps, no fusion line with, you know, variations in structure and composition, you'd think that's going to be great, that's going to be better. But I'm sure the experts in that kind of technique will probably tell us other things that can go wrong. So I think I'll probably take that question away with me and see if I can find any more information on it.
Fantastic. Thanks, Mike. Okay, brilliant. Great to see you again, Mike. And thanks very much
you too.
For popping in to do this. We'll be in touch in the new year and talk about the way forward with some kind of corrosion course. So
yeah, it sounds good. And stay well, Mike, and everybody else.
Yeah, take care, Mike. If I could ask you to stop sharing your screen, please.